Welcome to a lesson on triple integrals using cylindrical coordinates. The goal is to set up and evaluate triple integrals using cylindrical coordinates. In the cylindrical coordinate system, a point P in space, as we see here modeled below, is represented by an ordered triple r, theta, z, where r theta is the polar representation of a point in the xy plane, where r is a directed distance from the origin in the xy plane, as we see here. Theta is the angle counterclockwise from the polar axis, or positive x-axis in the xy plane, as we see here, and z is the directed distance up or down from r theta to the point P. We also need to be familiar with the formulas used to convert between cylindrical and rectangular coordinates, as we see here and here. So if you don't already have those in your notes, you may want to write those down. Now let's talk about converting a triple integral in rectangular form to cylindrical form. The first thing we should notice here is that f of x, y, z must be written as f of r theta, r sine theta, z. So to convert the rectangular equation to a cylindrical equation, we replace x with r cosine theta, y with r sine theta, and z remains z. And just as when we were dealing with polar coordinates, differential v gives us an extra factor of r, and then dz, dr, d theta. So if the solid region of integration can be easily defined by using cylindrical coordinates, the result of the triple integral is often much easier to evaluate. And when converting from rectangular to cylindrical coordinates, the x, y, x, z, and y, z traces are often helpful. Let's go and take a look at our first example. We want to integrate f of x, y, z over the solid region V bounded by z equals 0 and z equals 4 minus the square root of x squared plus y squared. Let's look at this graphically. So our region of integration is the solid region inside this cone above the yellow plane. So z equals 4 minus the square root of x squared plus y squared is this cone here, and z equals 0 is this plane here. If we wanted to sketch the xy trace, we'd take this equation here and replace z with 0. So if we did that, we could move the square root to the other side and then square both sides. That would give us x squared plus y squared equals 16. So we'd have the circle here centered at the origin with a radius of 4. So this would be 4, 4, negative 4, and negative 4. Let's see if we can use this information to set up our triple integral using cylindrical coordinates. Well, first our function f of x, y, z is equal to x squared plus y squared. Well, x squared plus y squared is equal to r squared. So we'd have r squared. Then remember, differential v gives us an extra factor of r, dz, dr, d theta. So for the limits of integration for z, we can see that z starts at 0 and goes up to the surface. So the lower limit is going to be 0. The upper limit is going to be this surface here. And since r squared is equal to x squared plus y squared, we'd have 4 minus the square root of r squared, or just 4 minus r. And then to determine the limits of integration for r, we can take a look at the xy trace. We can see that the radius r starts at 0 and goes out to positive 4. And then for theta, because we want this entire cone, we would start at 0 and rotate all the way around to 2 pi. So the lower limit for theta would be 0, and the upper limit would be 2 pi. So our integrand is going to be r cubed. And then we have dz, dr, d theta. Let's go ahead and evaluate this on the next slide. Integrating with respect to z, r is treated as a constant. So we'd have r cubed z. Now we'll replace z with 4 minus r and then 0. So we'd have r cubed times 4 minus r, and then when z is 0, it'd be 0. Let's go ahead and distribute here. We'll have 4r cubed minus r to the fourth. And now we'll integrate with respect to r. So we're going to have 4 times r to the fourth over 4. That's going to give us r to the fourth. We'll have minus r to the fifth over 5, or 1/5 r to the fifth. So when we sub in r equals 2, we're going to have 16 minus, this will be 32 fifths. And then again, when r is 0, these will both be 0. 16 minus 32 fifths, that'll be 48 fifths. Now we integrate with respect to theta. So we have 48 fifths times 2 pi. Put this over 1, it's going to give us 96 pi fifths. Let's go and take a look at another one. Here we want to integrate f of x, y, z equals 1 over the solid region V bounded by z equals 0, x squared plus y squared equals 1, x squared plus y squared equals 4, and z equals 4 minus the quantity x squared plus y squared. Let's start by taking a look at a graph of this. So our region of integration is between the two cylinders, below the blue surface, and above the yellow plane. So let's go ahead and set this up using cylindrical coordinates. Before we do that, let's go ahead and label a few things. Before we do that, let's go ahead and label a couple things here. This surface here in blue is z equals 4 minus the quantity x squared plus y squared. If we take a look at the xy trace, the smaller circle here is x squared plus y squared equals 1. And this larger circle is x squared plus y squared equals 4. So this time f of x, y is equal to 1. So differential v is just going to be r dz dr d theta. And now for the limits of integration for z expressed as a function of r and theta, going back to this graph here, we know now we can replace x squared plus y squared with r squared. So z is going to start at 0, this yellow plane, and then go up to the surface, which will be 4 minus r squared, using cylindrical coordinates. And then for r, looking at the xy trace, we're integrating over the solid region between these two cylinders. So r is going to be from 1 on the red circle to 2 on the black circle. And then for theta, we want to go all the way around the circle, so it's going to be from 0 all the way to 2 pi again. And we're going to see in the next video, when f of x, y, z is equal to 1, as we see here, this triple integral will actually give us the volume defined by these limits of integration. Let's go ahead and first integrate with respect to z. So because r is treated as a constant, we'll have rz. So we're going to replace z with 4 minus r squared, and then with 0. So we're going to have r times 4 minus r squared. That'll be 4r minus r cubed. And then when z is 0, this will be 0. Let's go ahead and finish this on the next page. Integrating with respect to r, that's going to give us 4 times r squared over 2, or 2r squared, minus r to the fourth over 4, or 1/4 r to the fourth. And we replace r with 2. Here we're going to have 8 minus, this will be 2 to the fourth. It's going to give us 16 divided by 4, that's 4. Minus, and then when r is 1, we'll have 2 minus 1/4. It's going to be 4 minus 1 3/4. That's going to give us 9/4. So we'll have 9/4 times 2 pi minus 0. This will be 18/4 pi or 9/2 pi. And again, because f of x, y, z was equal to 1, this actually does give us the volume defined by the limits of integration. In the next video, we'll discuss more about determining volume using triple integrals. I hope this was helpful.